Good morning, everyone. I'm Dr. Maha HAWARY from the Faculty of Science at Mohammed V University. It's a pleasure to be here virtually and present our research titled Evaluation of Corrosion Effects in Stainless Steel, Aluminium, and Copper during Sunflower Biodiesel Production. In this presentation, I will begin with an introduction that covers the problem and the objective of our work. Next, I will explain the materials and method used in our study. Following that, I will discuss the results and their implication. Finally, I will conclude with a summary of the key points and the significations of our finding. By definition, a biodiesel is a renewable, biodegradable fuel from vegetable oils, animal fats, or waste cooking oil. It can be used in most diesel engines without any modifications. Biodiesel is a non-toxic, clean, burning fuel that produces fewer emissions than petroleum diesel. But metal come into contact with biodiesel can be corroded from the first step production to storage than the last one used in the engine. This problem is due largely to the unique chemical composition of biodiesel, which can accelerate the degradation of materials. To ensure the reliable use and the efficiency of biodiesel in variety of applications, it's essential to understand and reduce the corrosion phenomena, and this is our objective. In this study, we aim to investigate the three mentioned materials during the biodiesel production with the experimental setup, which is a potentiostat OregaFlex piloted with a computer equipped with the Orega Master software, with the cell containing 3 electrodes, an auxiliary platinum electrode, reference electrode, and the work electrode with a working area of 1 centimeter square. The electrochemical measurement used in this study was the open circuit potential and the electrochemical impedance spectroscopy. The evaluation of this potential reflects the interaction between the electrode and its environment, indicating its stability and reactivity. The ES data provide valuable information on the electrochemical processes that occur at the electrode-electrolyte interface, enabling a corrosion mechanism to be understood, a surface condition to be assessed, and the materials and the process to be optimized. In this study, various characterization techniques were employed to analyze the property and the behavior of biodiesel. FTS spectroscopy provides insight into chemical bond and structure. The GCMS identify and quantify a compound and biodiesel, and the ultraviolet visible spectroscopy and the FEAS was used to identify the concentration of elements released in the corrosive solution, where the Durex and the same was used to study the morphology and the elements of the composition of the metal surfaces. Move on to the part of results and discussion. The study focused on the application of the trans-acidification process to produce biodiesel involving the use of sunflower vegetable oil, methanol, and the kawash as the base catalyst. The result provide a good illustration with yield of 93%. The table show the physicochemical parameter. As we can see, there are a conforms with the established standard. The GCMS analysis was used to characterize our sunflower biodiesel after the test. It reveals a 5 compound, of which methyllenoniate is the main compound. The FTS spectrum of biodiesel clearly show 2 main peaks, a largely peak attributed to the CO stretching vibration of the ester group as the primary compound of biodiesel, a sharp peak attributed to stretching vibration of methyl group ester group as a second compound characteristic of biodiesel. It also show a characteristic peak of 4 for the OH pound of glycerol situated in 32 to 3400 centimeter region. The electrochemical measurement show a flat capacitive semicircle and Nyquist diagram indicating a surface inhomogeneity. Stainless steel and aluminium's corrosion resistance improves over time, likely due to the passive layer formation. After 65 minutes, aluminium and stainless steel continue to improve their resistance, while copper remain unstable, associated with a development of a protective layer. DES parameter was determined by simulation using electrical model. A biodiesel exhibits elevated solution resistance, which is increased over time, suggesting a reduced corrosion activity. The resistance to corrosion product ERF is significantly higher than the resistance to charge transfer, indicating that the metal corrosion resistance is mildly influenced by the protective film formed on the surface. As we can see, the aluminium exhibits a higher RF resistant corrosion, which means high protection. The ES, the ultraviolet visible spectroscopy, exhibit a higher corrosion and the metal loss due to biodegradation for the copper surface. The stainless steel biodiesel intensified excited oxide peaks, iron and chromium, indicating a strong protective film, possibly from biodiesel breakdown product. The aluminium initially protective oxide layer weakened by biodiesel, but then reformed, suggesting improved corrosion resistance in the long run. The EF analysis confirmed the higher copper released compared to aluminum stainless steel, which with nickel and chromium below the detection limit, indicating oxide layer protective formed on the surface of the metal. The ultraviolet visible detects significant copper oxidation, while stainless steel and aluminum showed a minimal oxidation. Where the surface characterization by the same analysis revealed the following key findings. Aluminium developed a protective oxide layer covering 85% of its surface. This oxide coating increased increased contact resistance and significantly reduced the material deterioration. The EDS analysis detected corrosion products containing carbon and oxygen on stainless steel, indicating a compromise of the passive layer. Reduced oxygen environment confirmed the better preservation of the passive layer, thereby minimizing corrosion. The CM analysis of copper showed a corrosion product on its surface. The fatty acid composition and the profile of biodiesel play a critical role in activation oxygen atom in biodiesel, leading to the metal formation. The X-ray diffraction analysis showed a significant oxide formation on aluminium, stainless, and copper surface in biodiesel. Aluminium exhibits a robust protective layer of aluminium hydroxide and oxide, resisting biodiesel-induced acid corrosion, while stainless and copper showed a significant oxide formation, indicating a corrosion process. To sum up, the results demonstrate that the strength and the resistance of aluminum in corrosion environment, as well as the effectiveness of protective oxide layer in improving the metal's durability, which suggests that aluminum is the preferred base metal for biodiesel synthesis. Thank you for your attention.